So this is the last talk of the Congress conference. Dennis Sullivan, and he will speak about string topology and three manifolds.
How many of you were here at the 10 years ago at the 60th? Too many.
We forgot.
Well, this is some borrowing from Barry Mason, which is this is how to really do a superlative. So it's his idea, not mine, but we can apply it to Alberto. So if you talk about animation, an animator in mathematical sociology, Alberto is clearly the best in the world today. But probably the best there ever has been. And the best there ever will be. That's the so sorry for that. I said 10 years ago.
I sent it to you.
All right. So, okay, so we've done so many good talks. I'm worried about this talk. It'll look bad, but it's okay. So I decided to talk about some very beautiful mathematics. So it'll help. So let's start with a little bit about three manifolds. So there are these three-dimensional geometries. Keep this undefined for a little bit, but there are. Let's see, maybe I'll do this in the middle here. Geometry. So there are 8 of them, but there are 5 plus 3 geometries. So these are, so 3D geometry means there should exist a simply connected three-dimensional Riemannian manifold which is complete, and it's homogeneous in the sense that locally homogeneous. Every little point, a neighborhood of every point and the neighborhood of any other point are isometric. Not by global isometry necessarily, but there's little isometry here that takes us over. So the terrain looks the same. And they should admit this simply connected thing should admit a discrete, properly discontinuous group of isometries so that the quotient is compact. So that's the definition of a three-dimensional geometry. And there are eight of them, essentially, 8 types. And this dichotomy here is this type here admits compact quotients, which I just described. If you have such a discrete group, you can take the quotient and then get a compact manifold that has locally homogeneous, right? But 3 of the geometries, they also have compact, but they also have finite volume, non-compact. So they're finite volume, non-compact. And these are, I'll just give the geometry upstairs. So you have three-dimensional hyperbolic space, two-dimensional hyperbolic space cross R, and then you have SL2R, the Lie group, put some left invariant on it, and then take a universal cover to make it simply connected. So those are the geometries that have both this and this. And then you have 5 geometries. You have, well, S3 is the only compact one, and then R3, and then N is the 2-step nilpotent group. The realization is R2, and 1R in the center, and then you have the 3-dimensional solvable Lie group, which is unimodular, which means the left arm measure equals the right arm measure. The arm measure, the invariant measure is invariant under the left invariant metric in volume form is invariant under also right translation. And that's, no, there's one more. Oh yeah. S2 cross R. So those are the 8 geometries written that way. And then put the 5 here and here. So then all of these geometries, so these only have compact quotients, not finite volume quotients. And here the pi 1 is, I'll put solvable in quotes. That means subgroup of finite index is solvable. So if I put something in quotes that's about groups, it means maybe it has to a subgroup of finite index. So here pi 1 is solvable. For these 4 it's abelian, for these, and this one is, sorry, for these 3 it's abelian, and essentially, and this is nilpotent, this is solvable. And then these are not solvable with quotes. Let's see. What else? So these, oh yeah, I did. Right, so these are characterized by pi 1 is essentially solvable. And then, now, when you realize manifolds, there's sort of, there's sort of two kinds of geometries, pure and mixed. So pure means it's a compact manifold, and at every point is locally like every other point. That's one of the 8 geometries is appearing here. And so, of course, all of these are pure. Because if you have one of these geometries, you already have a, well, I mean, they all are pure. There's no way to get them otherwise. And then, so these.
So what was pure again?
Pure means not mixed. Maybe I should say what mixed is.
Isotropic?
No, pure means that the whole compact. Now let's talk about compact manifolds. This is a picture of closed 3 manifolds. So does the closed 3 manifold admit one geometry which is locally the same at every point? Then if it does, I say it's pure. Okay. So those are the pure. So all of these 5, they give you pure examples, right? But you can also get a few from here. You can get, let's see, we have H3, H2 cross R, and SL2R. These 2 here, yeah, I forgot to say, these 2 here, when you look at the compact quotient, or when you look at the quotients, these are examples of Seifert vibrations. So this could be like a Riemann surface of higher genus across a circle, and then this could be some circle bundle over Riemann surface of higher genus, or with ciphered fibers, or over an orbifold, various types of things. These are all cyclic vibrations. And these finite volume examples, so this looks a lot like Pablo's talk. That's the right thing, right? Pablo Flores, right? That was your talk, right?
Yeah.
Right. These finite volume manifolds, and I wish I had little software to blow up this circle. Blow this up, you actually see a torus. This little ring here, torus. So there's like a torus here. All of these, and this torus is shrinking exponentially fast in order to make the finite volume. It's going to infinity to make it complete. So these manifolds all look something like this. They have toroidal ends, these things here. And so that's how you can make mixed examples. If you take any graph, and this also fits with Pablo's talk, so it makes a specific kind of a graph. So you can take like a graph like this, where the vertices here. Well, there's a curious point here that if you took a surface cross R, surface cross the circle with punctures. So if you take a Riemann surface with punctures, now this is now a realistic drawing. This is now a circle. Then you take a circle bundle over it. This circle bundle will have these toroidal ends, and you still have finite volume. But if this were a trivial circle bundle, you could put this geometry on it, or in fact, any oriented circle bundle over a manifold with boundary actually is trivial, because a circle bundle is classified by a two-dimensional homology class. So these things here on the open manifolds are actually product bundles, but they have SO2R structure. So a thin cross S1 could either have this structure or this structure. It's not determined by the topology. So I'm going to group these two together and just call them ciphered vibrations. And then you kind of, sometimes you have to use this one, but sometimes you can use this one or this one. Depends on if you have special fibers or not. Okay. So then this graph, and so I'll refer to these with the letter S, a lot of S's here, and refer to these kinds with the letter H. So this graph is labeled. I'm going to put an H there, and an S there, and an S there, something like that. And then you have to sort of repeating the pictures from Abel's talk. So these are these three manifolds with finite volume geometries coming from there, and I've grouped two of the three into one label S, and then the other one I call H. These are the three geometries, so it's really 1 plus 2, you could say. But this is big 2. And then you glue the toruses together. And there's more data you need here. You need a matrix in SOTG to glue this torus to that torus to get the topological three-manifold. And so this is what a mixed one looks like. Well, pure one just looks like the geometry is the same everywhere. It's compact. And the mixed one looks like this. This is still compact. And this decomposition, as long as you take it minimal, then it's unique. This decomposition is unique. The graph is unique, and the labeling is unique. as long as you take the smallest one, it'll be unique. So, and then, I should have started with, so then the Thurston geometrization, which he actually proved in this case, basically these cases, well, except for the Poincare conjecture, one of the 5 here, and some of these cases, is that every prime three-manifold, closed three-manifold, admits these nice geometries in this sense. Either it's pure or it's mixed in this sense. And then prime means there's every closed three-manifold is a connected sum of primes. It's a connected sum of closed manifolds which themselves cannot be written as a non-trivial connected sum. They're called primes then, and of primes. And then every prime is admits this one of these 8 geometries. If it's a pure case, or if it's a mixed case, it has these kind of canonical graph, and then these 2 things. What time do I start? Did I start?
I think you started at 12:20.
12:20. Okay. Great. All right. So it's the 3rd time there. Okay. Now the kind of ideal picture of why this happens is that you just take your closed three-manifold and you put any Riemannian metric on it, and then you start applying this kind of nonlinear PDE, which is sort of like a heat flow. And this flow, it has a name, and it's a flow on the space of Riemannian manifolds. And then what happens, this is an ideal picture of what happens. Some of this has been proven, but not all of it's been proven. I'll just pretend it's all been proven. It's an idea. The idea is, first thing that happens is that little I guess I'm not even loose. So anyway, you imagine you have some connected sum decomposition. These could be complicated, but anyway. Some spheres appear, and the geometry has some minimal spheres that are small 2 spheres that are the 2 spheres that separate the connected sum decomposition. And once they form and they get positively curved, then they quickly, in finite time, crush the points. They pinch off, so you get kind of a necklace. And so you get the decomposition into primes produced by the flow. And then you can cut, and then you can look at one of these primes, and then you continue the flow, and then it's like, again, related to Pablo's talk, that then it sort of partially collapses into lumps and 1 and 2-dimensional pieces. The lumps correspond to, these 1-dimensional pieces correspond to these things. And then two of these three geometries, or the two that I looped into the S's, they collapse the circle fibration. The circle shrinks and they collapse down to two-dimensional things that look like planar with small little circles in them. And then the hyperbolic pieces stay nice and fat, volume stays there, and the thing becomes hyperbolic. So that's kind of an ideal picture of, and these pictures started emerging with Cheeger's thesis in the 60s, and then Gromov developed limit ideas and Gromov metrics and big long development. A lot of it was done in Stony Brook. So I kind of was visiting there in summers and kind of hearing about it all the time. And then, well, you know, when you hang out with Alberto, Thursday and Friday you try to show that you can't have a minimal flow on S3. And then, well, actually, no. On Thursday and Friday, you work on the Poincare and then, well, okay, you can't prove that. Well, let's assume it's S3. Then, okay, let's prove something about S3. There's no minimal flow on S3. Try that for the weekend. And in some sense, I think maybe this idea kind of emerged with Alberto's. Why should the Poincare conjecture be true? Should be true because there should be some theorem about three manifolds, and just when they're simply connected, it forces it to be the S3 because of this theorem. So that was an idea floating around before Thurston thought of his geometrization. In fact, I was visiting him for a semester in '76, and we talked about these ideas that I proved something about three manifolds. And one great thing, which is still open, is which three manifolds exist in formally flat structures. I don't know if there's an answer to that yet. This is a precise prediction. But that would have been a great thing to prove. Every three manifold, this is false, every three manifold has a conformally flat structure. And there's some evidence that this is true because it's closed under connected sum, that property. Hyperbolic manifolds have it. And then unfortunately, Bill Goldman, who was an undergraduate when we were trying to prove this, showed that these guys don't have it. Anyway, but that would have been a theorem if you could prove every three manifold has a conformally flat structure, then you just look at the developing map or something connected one is S3. So that's proved quite great here. So this vision of Thurston, the geometrization, is proving something or stating something about all three manifolds that can be proved. And then he proved a big piece of it, which made this statement very likely to give it a good chance. And then 20 years or 10 years later, well, I think that's when Hamilton started his Ricci flow analysis. Thurston made this sure. And then made a little progress for 10 years, and there was no progress for another 10 years, and then Perlman picked it up and finished it off. The main idea is controlling the geometry and doing these cuts. And then he doesn't prove this whole ideal image, but he proves enough of it to get the result. I think that's a summary. Okay, a little too much time on that. Okay, so now here's the question. So three manifolds are kind of, you can list them, or at least put them in boxes. And, oh yeah, there, you could have an H and an S also, one of these S's. A graph could just be one, it could be pure, or you could have one of these 5 other pure geometries. So really all 8 geometries can be pure geometries by definition. And I want to call this information here the form. This is definition. The form of geometrization. So the form of geometrization is you take a three manifold, which is a prime. Imagine this first step has been done. I mean, although this has to be. So you see, oh yes, another point. This audience some of whom are part of which is dynamics. I mean, this flow is a flow on the space of geometries, so it's an interesting dynamical system. So since there isn't a unique place to end up, because you have these two choices here, but it's sort of finite dimensional. I mean, there's a sort of finite dimensional set of places to end up. There's kind of an attractor here. So there's interesting dynamics, and there'll be different domains of attraction depending on what kind of geometries you end up with there. So there's an interesting dynamical system to be analyzed here, which is somehow at the level of difficulty of three-dimensional hydrodynamics, which is totally going to solve. Okay, so anyway, so since the definition of fun, and then the question is,
So the form of geometrization was,
excuse me?
what was the form of geometrization?
The box. The information provided by the box. It's given a prime three-manifold. It lands in one of these unique places. And this information, the graph and the labeling on the graph is unique if you choose it minimally. And so the question is, so suppose you're given a prime three-manifold. I'm going to say, well, how do you know it's prime? Well, if you're given a three-manifold, I mean, it's hard to know. I mean, if it is a connected sum, then the fundamental group is a free product. So, and for these primes, it's not a free product. So that's one way to tell whether the manifold is prime or not. The fundamental group is not a free product. Okay, but given a prime three-manifold, how can you recognize? Can one recognize or compute the form of geometrization? So, like the reverse of Pablo solving, one of these graph manifolds, suppose you, for a three-manifold, if you say you're not in these cases in prime, you have to have one of these graph manifolds. So how would you tell what the graph is and what are the hyperbolic pieces and stuff like that, right? So how can one yeah. Okay. So that's what I want to talk about. So, so first step is you could see whether or not, see if pi 1 is virtually solvable. I hate having notes. Decide if 5 or 3. You decide whether or not you have even 5 or 3. Whether you're in, whether you're in these 5 special geometries or you have this 3 type over here. So if you're in the 3 type, looks like this or this. See, none of these groups are solvable. And then it's all solvable. So if it is solvable, you're in this 5 case, and then you can just look at the structure, and then you can just look at some simple things. And for example, if so you look at then you look at the first Betti number. If the first Betti number is 0, 2, or 3, then this corresponds to the S3 geometry, and 3 corresponds to the flat geometry. So it's covered by 3 torus, and then 2 would be the nil geometry, covered by the Heisenberg Lie group. And then, if you look at this, it's either this, or it's 1. Turns out, just by looking at the list, in this case, it's either S2 cross, like R is the geometry, so the manifold is like S2 cross S1. I could say what the manifolds are, up to finite cover in gamma, or it's 3 sphere up to taking finite cover. And then if it first beta number is 1, and this has pi 1 as Z, of course, or it's this one of these solved manifolds, which is like a mapping torus over the circle with a fiber of torus, and the monodromy is hyperbolic conjugacy class in SL2Z. So mapping torus of an Anosov diffeomorphism. So this thing, the pi 1, has exponential growth. This has growth r to the 4th, cubed, or n to the 4th, n to the 4th, n cubed, at 0, 1, whatever. So if it were solvable, then if you knew so you can look at the first beta number, there's only 4 possibilities. The beta number then tells what the possibility is in 1 or 2 cases, but then there's a big split between this is a very small manifold, it's a very big manifold. Okay. Discuss this a second way later. Well, we probably won't. We could. I don't know if it's the time. So, there's a little issue here because, we talk about pi 1 and so on, but it's not something you can compute. You can write presentations for it. So if it were something very simple like this, then you might be able to recognize it. So then you might know this. Right? There's a question of how you know things. What does it mean to recognize what you're allowed to know? So we'd like to touch the fundamental group in a way as little as possible, because that's essentially an undecidable realm of mathematics. So then, if 3, we're in this 3 case, if 3, I'm going to take so you can remember which 3 I mean. If 3 then we're going to use string topology. And actually, we're going to use string topology of N3. Try to see what the form, so we eliminated these now, so we're in this case. This is the 5 case, the 3 case. This is the 5 case. So we want to see whether it's a pure hyperbolic manifold, a pure ciphered manifold, or it has a graph like this. So this string topology is like using pi 1. So we use string topology. So using string topology is like using pi 1, but it's softer. A little softer, and it sort of uses Poincare duality. So it's sort of more manifoldy type algebraic topology. So that's kind of how I kind of think of it. And I guess I'll try to leave that over there and keep using these boards. two kind of string topologies that are going to be used here. So this, and what I want to discuss. Traditional and call it stratified. So, I mean, what I'm trying to get to, I may not do too well, but one way to give yourself prime three manifold is to cut a knot out of S3. I should say that I've expressed all this for closed manifolds, but you can have, this also applies to decomposed manifolds with torus boundary as long as the fundamental groups of the boundary inject. So the decomposition applies the same way. Just that in this, like you might cut it off here, this would be a manifold with one torus boundary component. So it's the same theorem, just you have some free edges of the graph. So, for example, a link complement would be, give yourself a link, and that gives you a manifold with several boundary components, and then it'll have a geometrization like this. And what is it? Of course, it could be like that or like that. Just like this. The graph could have one vertex. So the first part I'm going to state two theorems now. In the first one, I'm going to use what's called traditional string topology, and then in the second one, I want to use this newer kind of string topology. Okay, so the traditional string topology that I'm going to use is the following. There's a sentence here. There is a graded Lie algebra structure. We're doing some algebraic topology which is adapted to this problem. There's a graded Lie algebra graded Lie algebra structure finds on classes, equivalence classes of families of closed strings in M. So this is part of traditional string topology. So I'm going to draw the picture, which is the string topology part, which is using Poincare duality and kind of homological ideas, which are softer than pure pi 1 ideas in a way, although kind of sneaking into pi 1, backing into pi 1.
What do you mean by softer?
What do I mean by softer? Somebody asked that?
Yes.
Okay. Like a woman is softer than a man. I don't know. I'm more algebraic, functorial, more algebraic. Hopefully, I don't know what I mean to say. Abstract group theory, I mean, I don't know how to say it formally, I know what it intuitively, but abstract group theory is hard at. I mean, it's hard, because it's not even decidable. You can't do it. And I'm not saying this is decidable either, but it's sort of closer. It's sort of, okay, here's an example. Instead of studying a group, study its category of representations in the derived category. That would be softer. It has different properties. Doesn't really reconstruct the group only in certain settings, but it's like take the homology. It's a little softer. All right, so families of, so I'm going to do two one-dimensional families, and we're going to do a three-manifold. So we have, so it's hard to draw. I've got to draw two one-dimensional families. So a one-dimensional family of strings is a map of a one-dimensional family of circles into the manifold. So it's a surface mapping the manifold. I'm just going to draw a piece of the surface here. And here are the strings. This, and then I maybe have another one. I'm just drawing a piece of it. And then maybe it's circles going like this. And then you look at the intersection of these two surfaces. It goes like, well, let me draw it. The intersection of the two is like that. And then you look at this intersection. I mean, this is just a piece. I'm actually imagining, well, so I'm imagining, so this is the intersection, and then this is really part of the closed string. So this is like this, take a point here, and then there's a string going off like that. It's also part of the closed string. And so that one's going like that, that one going like that. And then at this point, now you use the operation of pi 1 at this point. Here's a loop, here's another loop at the same point. Oh, maybe turn the arrow the other way, look nicer. Then you make a new string at this point, which is go around like this, and then you go around the other one, and you come back like this. So you combine the two strings, and you get a one-dimensional family of strings. So given two one-dimensional families of strings, we have one-dimensional family of strings, tensor one-dimensional family of strings, and you get another one-dimensional family of strings. Now let's suppose these families are, in the one-dimensional case, are actually cycles, the one-dimensional cycles, so they're unions of circles. Then you would intersect them and you would get a bunch of unions of circles, and so you'd have a map from cycles of closed strings to cycles, tensor cycles of closed strings and the cycles of closed strings. And so if you call this family A and this family B, we have this at every point. Then this would be the bracket A with. So it turns out this is passed to homology classes of families of closed strings. So that means two circles of closed strings would be homologous if there would be a surface running between the circles and over every point of this. And the family of closed strings would extend as the family of closed strings to the surface. Closed string means a map of the surface. So that's the algebra structure. And if we're over here in 5, well, this case is a little special. It's not, what I'm going to say now isn't true. It's slightly off. Sometimes it's not true. Let me eliminate that from the discussion. We'll pretend we'll do that later. But then what happens is that, so what you get, if you call this the homology classes of one-dimensional families of vector space, call it V, or maybe we call it L1, so like the three-loop space. So L1 is the one-dimensional families of closed strings, and this gives a map from L1 to L1 to L1, and this satisfies the Jacobian. Homology classes. And let L0 the zero-dimensional homology classes of closed strings. So that means we'll have a point then in the closed string and manifold, and the homology, one-dimensional homology would just be an interval plus some circles north, and two endpoints would be freely homotopic closed strings. So L0, the zero-dimensional families of the homology, is just the vector space on pi hat. So pi hat is equal to the conjugacy classes of pi 1. So this is fitting with this idea of what softer means. The representations of pi 1 would care about the conjugacy classes, like traces and things like that. And so I'm only going to use the set of conjugacy classes, not the whole group structure. And also we're going to need to know the power law operations on here. That much of the group structure we're going to use. And this turns out when you do this, when you intersect a one-dimensional family with a zero-dimensional family, then the surface of the one-dimensional family might intersect. It's like if you have a knot, so something like this. Yeah, all right, so something like this. So this is these two things here. If you pull this over to here, that would be a one-dimensional family, and you see it intersects at one point. And so this would be an element in the one-dimensional family, and this would be an element in the zero-dimensional family, and then where it pulls across, you would get an intersection, and you would form this product, get something here. Right, so it measures how things are linked and tangled in the three-manifold. But it's organized into a nice Lie algebra structure. So this is a module. This is a Lie algebra, and this is L naught is a Lie module. And in this case here, there's another group dimension 2 sometimes. Let's leave that off. So,
One question.
yeah.
How do the subsequent pieces show up in the string topology?
Oh, I'm getting to that. That's the whole point of the talk. Yeah, I'm about to state that now. And then, gotta get going here, though. So,
Just give your time. Don't worry about the time.
It's 35 minutes.
all right. My wife, I talked to my wife, and I'm thinking about her right now because she doesn't like me to go over good thoughts, even when she's not there. So I'm always worried about it. She told me this morning, it's lucky you only got there for a day and a half, so that's enough for you. Too much chocolate. So, oh yeah. So let me define closed string structure. Closed string structure that's relevant for this recognition problem. So it's this Lie algebra here. I need the power law operations here. And I'll just say that. And then there's also a direct sum decomposition, because you see when you have a connected family of strings, all of these strings are conjugate. So they're in one conjugacy class. The components, so the homology is naturally, the space of closed strings has one component for each conjugacy class. And so the direct sum decomposition of this over the components. The Lie algebra doesn't respect that direct sum decomposition. I mean, it sort of respects it, but doesn't preserve it. So anyway, that's part of the structure. So there's the Lie algebra structure, the direct sum decomposition over pi hat, and then the power laws here, and then the power operation. So that's the closed string structure. Okay, and then there's a theorem. Almost on the archives by it's like theorem 1. This is by beloved Chas, the person I just referred to, and Siddhartha Gadgil. He's in Bangalore. That says the closed string structure, that closed string structure over there. Bracket, the direct sum decomposition over pi hat, and the power laws, power operations. So this is what I mean by a softening of pi 1. Plus finite grade values. See, it's not really using to deduce this from the fundamental group, but it's weaker information. This determines the form of the geometric figure. Well, let's say in 3. Case we're interested in. So it determines the graph and how you label the graph by either hyperbolic or these collapsible pieces. Okay, so I'm going to give some ideas of this. Very, very natural. And before that, I'm going to brush at the end. I just want to mention 2. Give ideas for proofs.
Can you re-explain what is the third piece of question in the third piece?
Excuse me?
What is the third thing you vote for?
What is what?
The third thing. There's the Lie algebra.
Third thing. Power operations on pi hat.
So what does it mean? What does it mean?
Yeah. What does it mean? It's trivial what it means, but I've always wondered what it really means. If you take a group, you form this set, called the set of consequences. And I say, what structure does it have? You can't multiply 2 consequences, unfortunately. But you can raise them to powers. So it's a set with that structure. And by the way, none of these groups have torsion. Because the universal covers are contractible. They're finite dimensional take on 1, so no element of finite order. Like form of homology. So, but then this structure here can be deduced from pi 1. This structure is not deducible from pi 1 as an abstract group. This uses the 3 method. I use now these circle families of closed strings. This circle has to commute with this circle to describe the torus. So they correspond to Z plus D subgroup. I have subgroups of about 2 in pi 1. And these equivalence classes of these rank 2 abelian subgroups are forming a Lie algebra. So that using the geometry of the 3 manifold. That's been traditionally called. So the other theorem 2 uses this stratified string topology. Well, yeah, so as I say, I've said it already, that we can apply this to manifolds with torus boundary pi 1 injects. So now let's consider like S3 minus a knot, or minus a tube around a knot. So that'll be a 3 manifold with torus boundary, and as you know, the classical one knows that if this is a non-trivial knot, that's equivalent to pi 1 of the torus boundary injecting into pi 1 of the complement. So the non-trivial knot is exactly a manifold with 1 torus boundary, to which we can apply this theorem. One can say more about the graph, but I didn't. You can say very precisely, but I don't want to say whatever. I can't remember now what it was. Anyway, so there's a. So, if we wanted to apply this theorem to this case, we would have to work with closed strings in the complement of the knot. I would have to sort of give myself the complement of the knot. So I don't want to do that, because I don't want to give myself the complement of the knot. I want to think of it as a knot in 3 space. So there's the knot. And now when you have a manifold and a submanifold, there's something you can do with open strings. This is a physicist's name, but what it really means is you have a manifold and a submanifold, and you consider curves that in the ambient manifold that start and end on the submanifold. Those are open strings. And if you have different manifolds, different components, it would be like a category. These are the self-mappings and the mapping from different components, like a morphism category. There's a lot of interesting algebra that starts appearing in open string theory. In some sense, there's an idea that open string theory determines closed string theory by some fancy Coxwell's construction or something like that. Or at least, anyway, so somehow these closed strings, or you think it's like a Lie algebra, which is kind of a communicative concept. And these things are like an associative algebra category. So it's a completely different flavor. Now, there's an interesting operation called cutting. This sort of a coproduct, which is you might take a family of open strings and make it more. It might actually cut through here. It might cut through this thing again at this point here, and then you could break it into two open strings. So you'd be like a coproduct. Given one thing, you get two things. And well, if in this case this could happen generically because it's codimension, but if the boundary conditions were like on a knot, this wouldn't happen generically. But if you took one-dimensional families, it would happen, just like before. And see, I don't have anything from L0 to L0 because two one-dimensional things are disjoint. You take families, you get some interaction. Assuming here the same thing. But this one has the property, this operation, the picture I had here had the property that if you had two cycles, the output was a cycle. Now this one turns out not to have that property. There's a boundary term because you can imagine a situation like this. There's a very tiny little intersection. And you can imagine a family where this pulls out and then it's just going like that and there's no intersection. So in the middle of the family there's a term created. There's a boundary term created. And it prevents you from defining an operation like I did here. And this type of thing has been bugging me since the end of the 90s. And usually in the last couple of years, based on work with some younger collaborators, there's a way out of this, and there's been some useful corollaries. And the idea, what you do is you eliminate the problem by eliminating. You just consider, see, here's an interesting thing that this is kind of very general. It's very soft, very kind of algebraic. As I mentioned in the blurb for this talk, same thing. This is a homotopy invariant. For dimension 3, it's still good, but for higher dimensions, I'm not going to detect anything beyond homotopy invariant. But you can do something else. These strings have, each one is not just a point in the root string, it could have a personality. It could be either embedded, or it could cross itself, it could have cusps, it could have normal crossings. And these strings here could come in normal or tangent, and all kinds of things like that. So the whole space of strings where you work is stratified by the personality of the point, so you could work in open sets where you remove certain strata of things you don't like. And that'll be a diffeomorphism invariant, because personality is a diffeomorphism invariant. And so you can get a lot more invariance by removing stratum and performing special operations that wouldn't normally be defined. So that's what this stratified topology is. So you have to use that. So actually, you have to take a frame knot. You can imagine we have a knot diagram and use the vertical framing. And then you only consider open strings that say lead vertically, go around, and come in vertically from the bottom. And whenever they happen to cross the knot, they cross from up to down. So we remove, we consider generic strings. That's removing a set of infinite codimensions, so it doesn't change any algebraic topology. Then you remove certain stratum where these conditions fail. And these will be open conditions. One from the closed subset of things. Well, morally open. Because you definitely just want it to be not tangent. And you can have it. Anyway, so you work with special subsets of strings defined by geometric conditions. And then this coproduct here is perfectly well defined. And this can be used. And then for this theorem, well, a student who finished last year showed that if you apply this to M3 cross M3, and the diagonal is the subset that you use, and you use open strings there, satisfying an analogous condition, that this coproduct, when you took its cobar construction and looked at its homology, this actually had different structure over the rationals for the two lens spaces, L7-1 and L7-2, that are homotopy equivalent but not homomorphic. So you can distinguish with this coproduct, in this case, with the stratification idea, you can distinguish that. So anything you do with this will be a homotopy there. The three manifolds, that's okay. Okay, so now I'm into my overtime. So anyway, so the theorem is, I'll just state it in words, and then, let me write it because I'm one of my co-authors with Unidad, M. Sullivan, and the other co-author. And so the theorem is that, well, there's a little remark you have to make, that S3 minus the neighborhood of K is equivalent to B3 minus an arc in the neighborhood. So you work with a knot like this, with boundary and the ball. If you remove, if you have a round knot and you remove a ball like this, what's left is a ball and a knot in the boundary, and the complement's the same. So that means, and then we work with these open strings here. Now, since this is contractible, you can move the endpoints to where they coincide, so they kind of form a cycle. And then I'll just write the statement of the theorem. This CS structure of S3 minus K, which is this stuff here, which by this theorem determines the form of generalization, can be constructed using from the algebraic topology of sort of transverse, in this sense I've described, open strings in S3 on K. So I'm not giving myself the complement, I'm only giving myself the knot in S3 and so on. By a cyclic construction. You make these things into cycles, and then you can, it's some kind of cyclic construction, algebraic cyclic construction. Some people call it cyclic bar construction. And anyway, by an algebraic topology construction. Anyway, in the proof, we had to give our own proof of some known theorems in such a way that we could, on this model, we could build the bracket. So there's an analogous bracket that's defined for these open strings. And it lives on this thing constructed from the open strings, and then from that we reconstruct this information. So that's theorem 2. So why don't I stop and you ask your question again?
How do you recognize the cyclofabric pieces in the string topology?
Oh,
And I guess, but I now have an addendum to the question.
okay.
Do they show
Wait for the
up
answer.
as,
Wait for the answer.
Asking me to answer your question.
do they show up as virtually abelian subspaces of Lie algebra?
Oh, well, there's a lot, this is on reporting of someone else's work, so I'm only,
And you didn't see the idea of the proof of
no, I haven't, no, I'm gonna say all the ideas, I wanted to state this theorem before I think I did answer. Okay, so a lot of this is pretty familiar to perfect three manifolds. In fact, Siddharth is kind of a three manifold expert, Orb is the string topology expert. Oh, and I should mention the thesis quite a few years, about 5 years ago, of the students, Jose and Abaspur, characterized just this kind of three manifold in terms of traditional string topology, a slightly different string topology. And the idea for that is this is a paper of 98 in the archives called String Topology by me and Chance. Let's see. So these one-dimensional, so these are conjugacy classes, and these are one-dimensional families of circles. It's a degenerate chain, otherwise it doesn't appear in the homology. The homology just sticks out elements. And, now, when you have there's a really neat three-manifold argument that every map of so we take one of these one-dimensional families, it's a map of a torus in here. You can homotop that torus. Either it's one of these separating tori, I call them quasi-separating, or it's a torus in one of the ciphered pieces. Turns out you can move it off. This is a
Yeah, because the center.
this argument where you make things transversal. You look at these walls and make things transversal. You get a lot of loops. And look at innermost loops since they bound this.
Because the center is not trivial, no?
Objective. Anyway, there's a beautiful argument where and then you sort of trade sides. It even works with general human physics. This is not a hard argument, but it's nice. I would give you a mini course of love this argument. Anyway, so you can homotop anything into the ciphered pieces. So if you only had H's, for example, then all these tori would be homotopic to these tori that separate.
Yeah.
And then there's no intersection, and this Lie algebra is completely trivial. But there's still an action here, and then let's suppose it were all H's, for example. Then you can start finding out how things are linked by considering classes that go across like this. Now, this is a powerful algebraic thing. I wanted to show this picture. There's a lot of string topology. And this Lie algebra was introduced by Goldman in the 80s for surfaces. And this example I like very much. Consider these two strings. So now you can have zero-dimensional families, and they have to interact in dimension 2. So here's an obvious pair of curves that can't be separated by homotopy. Intuitively obvious, right? But the homological intersection is 0. And it's plus and minus. It turns out when you form the two operations, that one plus that one, they're not conjugates. So you have plus one conjugate class minus another conjugate class. You get a non-zero thing. So this bracket is very non-trivial in dimension 2. And then if you consider Seifert vibrations over it, all of this non-trivial Lie algebra structure on the surface, if you just take the vibration over a one complex, that's trivial. So each circle lifts to a torus. So there's a lot of tori in the Seifert vibration, which intersect exactly the way their projections intersect now. So you get a lot of the rich Lie algebra structure on the surface quotient of the Seifert things lifts faithfully up into the free manifold. Yeah.
You can detect whether free manifold has a center, no? Because the S pieces have non-trivial center.
Yeah, right.
And
Use the sector center.
yeah, that's where your torus come from. Yeah,
In their proof, the center is both
exactly.
the danger and the good thing.
Yeah.
There are different ways to fiber a torus. So one torus gives you lots of elements because there are different ways of fibering it. Anyway, so in some sense, this Lie algebra is the direct sum over the Seifert pieces of non-trivial Lie algebras that are living just in the Seifert pieces. So that H1 is the Lie algebra splits as the direct sum of finite pieces. And then you study the how they're linked up by using this part of the structure. There's some non-trivial things about powers that have to come in after. That's the idea of everything. Addendum question?
You didn't answer the first question.
That was my answer. That was my answer.
So
Well, what did you say? What is the formula exactly?
whether they showed up as virtually abelian subspaces of the Lie algebra.
No, the opposite. Who's they?
The Seifert pieces.
Huh?
The
No,
Seifert-
The Goldman.
Yeah, I guess it's the
no, state the question. I'll answer that.
So you have a Seifert fiber piece.
You're formulating his question now, right? Wait, didn't somebody else ask a question? You were going to add an addendum, or you asked the first question? So you're doing the full.
I'm both of those.
You're both of those people. Okay. Sorry.
So the addendum was to
No, what's the first question though?
how do Seifert fiber pieces show up in string topology? And you've just answered.
Okay. Then what about this virtual abelian and something?
So if you have a Lie algebra structure, you might have abelian subspace,
Right.
or virtually abelian ones.
Yeah.
Live to finite coverage or just leave away. So those were the ones that are wondering if those were the ones that represent the Seifert.
No. So this is showing the Goldman Lie algebra of the surface is very complicated, rich structure, but it completely determines how sets of curves intersect, like Descartes decompositions, big structures determine the. And then when you have a Seifert vibration, you can form these one-dimensional families where the fiber is the family, and any curve down here is the lift, is the string. And then the way these two families intersect, just this simple computation in terms of how they intersect down on the surface. So the non-trivial structure on the surface gives you a very non-trivial structure in the Seifert piece. Okay, so you get a non-trivial Lie algebra here, a non-trivial one here, no Lie algebra here, no Lie algebra here in H1. So this is let's break this up into a Lie algebra and a Lie module. So this is my language. This is one taken together. It's one greatest Lie algebra. This is a Lie algebra. This is a Lie module. So the Lie algebra structure is the direct sum over the Seifert pieces of. Okay. These correspond to one-dimensional. Okay, these things correspond to a one-dimensional abelian sub-Lie algebra. Okay, because they don't interact. So there's your one-dimensional. So that's still there. And now you look at how. So and then you have non-trivial chunks of Lie algebra for each Seifert piece, and then you have this abelian piece here. So even if there's no Seifert, you have this abelian piece. And then now you look at how that intersecting with the zero components. So now you can then they have, algebraic criterion. So, this guy's connected to this. So if you take this guy here, then there'll be something, as I was saying, it goes like this and like this. Got to detect this, the fact that there's an edge here. And it's a little non-trivial because this point of is a plus and a minus, but you have to check the consequences are different, so you have to use group theory. So I'll just show that. Yeah, that's it. So.
Any other comments and questions?
Yeah, I have a comment. When in Madrid there was International Congress, Perelman didn't accept, but Hamilton gave a speech. He started saying, "I will never forget when Jim Eales came to my office and told me, why do you prove the Poincaré conjecture using analysis? Because
Without topology.
without topology, because you were there present.
No,
Because,
on the
because
internet.
topologists cannot prove it. So
And
I
what?
think
And what?
topologists cannot prove that. So should we-
Topology can't prove
can prove that. And that's the way Hamilton started. I almost jumped from my seat because I'm in debt to him. And in fact, I don't think sufficient credit has been given to him because he's the one that started.
no,
he's the one that started the harmonic band deformations.
Well, no, in this crowd here, Thurston gets plenty of credit because you know him. But, I go to lots of different crowds. They don't know from Thurston. They don't know about Hamilton.
Yeah.
So it's not true in other crowds.
Yeah. But I mean,
So I'm trying to write.
I mean Eales.
I'm trying to emphasize
No, but I mean Jim Eales.
Jim Eel. Oh, Jim Eel. Oh, yeah.
No, because Jim Eales is the one that told Hamilton that, no?
I see. Oh, okay.
Jim Eales told Hamilton.
No, that's not known.
No,
That's
Jim
not known.
Jim Eales is
That's
the one
Jim.
motivated Hamilton.
Hamilton said that in his speech.
Yeah, exactly. So,
But, I mean, Hamilton, the idea of this, and you say the idea of proving Poincaré conjecture, 3 is low dimension, so even though it's complicated, it's low dimensions.
Yeah.
So you should use that to prove it.
yeah.
So Hamilton does that. He computes the curvature tensor. It's very simple. It only has a few parameters in it. You can play around and prove things. So he gets information because it's low dimensional.
Yeah.
And then he gets a certain distance. So he understands this thing about the connected sum plot. That if this little two-sphere appears, a lot of people kind of understood that the strength is real fast. But then they couldn't control this nonlinear equation. They don't really have a good theory of nonlinear. There is no good theory, strong theory of nonlinear PDEs. So the reason this one is fairly successful is because it's describing a geometric object. And the geometry and topology of that object are crucial for the success of the thing.
Yeah.
So the statement that topologists can't prove it is not, they can help. And in fact, they need the help. And then these ideas of Gromov and Cheeger-Gromov ideas about geometric limits, and those ideas that sort of, this idea is not computing differential geometry in terms of curvature tensor, but thinking of the synthetic limits, which were part of the Alexandrov school that Gromov came from, and which, 20 years later, Perelman was the #1 guy.
Yeah.
So he came along and pushed that theory even further than Gromov and Cheeger. And then you add that, plus he understood Hamilton's work and added it in, added an idea from physics, about dilaton or something, and did this cutting, destroyed the analytic continuation by cutting, and proved it. So it's really a huge joint effort. But for me, before Thurston formulated this conjecture, for me, the Poincaré conjecture could either be true or false, and I think it used to oscillate every 10 years. Maybe we'll come up with an invariant, some quantum invariant or something that will distinguish some interesting simply connected manifold from 3-sphere. There's no reason for it to be true.
Yeah.
Unless Well, unless what happened or something like it. Namely, there's some theorem about all three manifolds that encompasses the statement. That's what happened.
Yeah.
So when Thurston formulated this, and he proved it, he proved this for all of these cases. And not complements, and complements, and the only cases he missed were this case and some of these cases, 1%. Well, now it's 0% because it's just a 5 theorem. That uses it. So he proved half of these things.
Exactly.
The Thurston proved half of these, this one, all of this one, and all of these. But not that one, which is
Not that one.
microwave conjecture. But now, well, look, I mean, this thing is like, this is such a big, incredible picture. If this were not true, now it would be sort of crazy.
Because it will be, in fact, an infinite number.
Yeah, well, this wouldn't be the optimal beauty of mathematics.
No.
Beauty.
Beauty, the answers.
Okay.
Any other questions or comments?
Let us try.
Let's thank the speaker again. And before we break for lunch, there's a little short presentation that one of our Italian colleagues would like to give. It was actually a